Good day, class. So this slide will now be on gas absorption and stripping. So this is the second of the 4 topics on the part 2 of the review session that we have in your chemical engineering review 4. Now, when we speak of gas absorption, it is a unit operation in which soluble components of a gas mixture are dissolved in a liquid solvent. Now, the inverse of this process is stripping, or what we call desorption. In stripping, we transfer a particular component of interest, a volatile component, from a liquid mixture into a gas solvent. Now, both these processes, absorption and stripping, in common with distillation, make use of a special equipment for bringing the gas and liquid phases into intimate contact. Now, absorption, stripping, and distillation operations are usually carried out in vertical cylindrical columns or towers, in which devices such as plates or packing elements are placed. The gas and liquid most often flow countercurrently, and the device serves to provide the contacting and the development of the interfacial surface through which real mass transfer takes place. Now, there are equations already shared to you in phase equilibria that we can make use together with material and energy balances in problems concerning gas absorption and stripping. Now, this particular equation now shown on your screen allows you to determine the solubility of any gas in water. Now, this is available in your handbook. What is good about this formula is you only need to know the mole fraction in the liquid phase of a particular gas to know its solubility. Now, this is only applicable for solvent water. Now, I have here sample problems that may look similar to the ones I have discussed already in class, but they are not. So they are provided with choices. However, as each of the choices are presented to you, there's only one that will give you the correct answer. Now, as to the solution of the correct answer presented here, it follows after the slide. So this particular part here was encoded using math type in Word so that it could be snipped and placed here on the side. So I leave it to you to read this part. Now, as to equipment selection, we can have plate columns or packed columns. So plate columns may be economical because it is often used in large-scale operations and are needed when we have a problem with so small liquid rates that the packing material for packed columns will not be adequately wetted. What we mean with adequately wetted is there's not enough velocity for your liquid, so as the packing material where mass transfer will occur are not all or are not uniformly wet for the phases to enable for specifically the liquid to transfer the component from the gas. Now, plate towers may be a better turn-down ratio, and since there are no packing materials, it's less probable to fouling by solids. Now, packed columns usually are chosen, so there's really the use for packed columns because we at times may need to handle, or the equipment may need to handle, corrosive materials or for liquids that foam badly. If we have also small or large diameter towers involving very low allowable pressure drops, so meaning we cannot bargain for very large pressure drops, then this particular column is for us to use. So for small or large towers wherein only allowable pressure drops are very small, it could also be used for small scale operations requiring diameters of less than 2 feet, or shall we say small towers in this case. So that's for your packed columns. Otherwise, we prefer plate columns because of this particular concern, and that is fouling in our packing materials should we use packed columns. Now, this is the gas absorption diagram, the schematic that is used by Giancouplis in terms of the absorption tower or gas absorption tower. So we number the stages based on the, or rather the phases based on the stage that they came from. So in the case of this V phase, it came from stage 1, so it's labeled as V sub 1. In the case of this liquid phase, since it is still about to enter the column and it's about to enter stage 1, then it is leaving stage 0. That is why it's having a subscript here of L sub O. The same principle applies for these two. Wherever they came from in terms of the stage that they are coming from, this one is Ln because it's coming from stage N. And this is V sub n plus 1 because this is the feed that is to be introduced into the column. Now, the way we number the stages, on the other hand, for the column is based on where the solvent enters. So, if this is the part where the solvent enters, the first stage is stage 1. This is the last stage in which your solvent leaves, so this is stage N. That's how we number based on John Copley's orientation. But if it's McCabe's orientation, the bottom is always 1, the topmost part of the column is always 2. Now, you have to note that John Copley's at times use in parallel that particular orientation. He may use this particular orientation. He may also use the orientation of McCabe specifically on problems using Krimser's equation. So 1 at the bottom, 2 at the top of the column. For stripping, we just change the identity of the solvent. So the stripper this time is the gas phase and the feed is the liquid mixture. So since the gas phase is our solvent, so the first stage is here at the bottom and the end stage is on top. The way we label the phases in terms of the subscript is still based on the particular stage where they are leaving. So V sub n for this, L sub n plus 1 for this one. For the feed, this one is L1, it's coming from stage 1, and this one is V sub O because it's entering stage 1. So still, we label this part of the column as 1, and this one is 2 for McCabe's orientation. So stripping uses a gas solvent stripping a liquid phase. Gas absorption uses a liquid solvent taking away a component in the gas phase. So that's the comparison between the two. Now, these are other types of columns and towers where gas absorption or stripping may be carried through. So you have here a trade tower. So you have the trays, you have a pack tower or a pack column, and you have packing materials here, which could either be random packing materials or structured packing materials. We can have spray towers in the case of gas absorption where the liquid solvent is injected into the column in form of sprays and the vapor is flowing countercurrent to the liquid that is going down. We can also have bubble columns where the liquid is uniformly introduced into the column while the vapor is bubbled up against this liquid that is going down. The uncommon type of tower, or shall I say separator, for gas absorption is the centrifugal contactor. The vapor actually is still introduced at the bottom part and the liquid is introduced on top through a central tube. But aside from this contacting, which is countercurrent, it is to be noted that the contact here uses the concept of the centrifugal force. So the liquid solvent is introduced downward while this particular equipment is rotating, making use of the centrifugal force. That way, the component from the gas could be transferred to the liquid solvent. So this is your centrifugal contactor. Now, for the material balance for gas absorption, if it's a single unit gas absorption equipment, you will label the phases based on the subscript of this particular single unit. So L1 for the liquid phase that leaves the stage, LO for the phase that enters the stage, liquid that is, V2 for the solvent that enters, and V1 for the solvent that leaves. You have to understand, and this is really to be emphasized, that the phases that are equilibrated here are the leaving phases or the exiting phases from a particular stage. So whether we're using a multi-stage process or a single-stage process like this, the equilibrated streams are the streams that leave a particular stage. In this case, that would be L1 and V1. In terms of the material balance, since we just simply have to add L sub O and V sub 2 and equate the sum to V1 and L sub 1. And when we have already this overall material balance for the two, we can pattern our other equations from this one. What I mean pattern, so if you want to use component balance on a particular component, though it is suggested that we base it on the solute that is to be transferred from the gas to the liquid solvent, then that should be XA and YA that you will be using as mole fractions to be multiplied to the liquid and the vapor phases respectively. So in this equation here that you are seeing, you have X for the liquid and you have Y for the vapor. And we use the subscript A because that's our solute, and we use also the subscript numbers representing the stage in which a particular concentration or phase came from. So L1 XA1 for the liquid phase leaving a single stage unit, and we have V1 YA1 for the vapor phase. You could see here an M. M represents the bulk phase, the mixture of the two phases where the interface, the real mass transfer occurs. So this is our bulk phase M. Should we have a three-component system, although most of the time we only have two components, the sum of the mole fractions of our components, whether that would be in the liquid phase or in the gas phase, is always equal to 1. So that's the material balance overall and component balance for our gas absorption process. Now, we have an option though in cases wherein both the overall material balance and the component balance equation will not suffice or will not allow us to solve what the problem requires. So in that case, we can have an alternative component balance utilizing not mole fractions but rather mole ratios. And aside from that, it's utilizing the inert parts of the streams. So L prime is the inert part of your solvent, especially if your solvent contains a solute, a little amount of solute. Now V prime is the inert part of your gas stream, which often is air. In the case of the L, this is often water. But in majority of the processes so far in gas absorption and stripping, the liquid solvent that is used is pure water. So automatically, the mole fraction, this mole fraction XAO initially is 0, and as such, this entire term will be 0. Now, I mentioned that in here, you're using mole ratio. Actually, this is the ratio of A to B in your gas phase V sub 2. So now it's mole ratio, not mole fraction. Now this particular component based on inert streams allows us to solve the problem even if we only get to know two mole concentrations, and the other one we get to solve out of the entire equation that we are provided here. So either of the two will lead to the other mole fraction or mole ratio, provided that of course the initial solvent that enters the column is a pure solvent. Now here is a problem on a mixture containing SO2, air SO2 mixture that wherein of course we need to take out SO2, and you are given the total pressure of the system in this value, the partial pressure of SO2, and the corresponding values of the feed and the solvent as they enter the column. You are to calculate the amounts and composition of the outlet phases. Now, in the last statement, you are to use the equilibrium data from figure 10.2-1. This is based upon Jankuplis. These figures simply approximate the nonlinear relationship between XA and P sub A for solute A in the system SO2 water. So in that particular figure, you'll be getting the Henry's law constant. Now, should you not want to use the particular equilibrium diagram, you can get it from property tables in your handbook in terms of the Henry's constant for varied or different systems. Now, this is the solution to that problem. It's not similar to the one that was provided to you. Just go through this. This was again written in Word file, then save in PDF, then snip so that it will fit in on the slide. So please read through this. This will simply use material balances, overall and component balance. Okay, that's it. Now, for multi-stage gas absorption processes or stripping processes, we label the phases in the same manner as we label them if we have only a single stage. You have LO here, you have LN here, you have V sub N plus 1 here, and you have V1 here. Your material balance, overall material balance, will still account the phases that enters and the phases that leaves, and still equate it to the bulk phase M, as you can see here. Then if we do overall component balance, this would be our overall component balance. Our M, in terms of representation, you can represent it excuse me, you can represent its concentration by X. So we don't use Y for the bulk phase, but rather it's the X. So this same principle we will apply just like in single stage absorption or stripping processes. Now, this is a tray tower snipped from the textbook by Jankuplis, and in here we can have the component balance using inert streams and utilizing mole ratios. So notice this is coming from Jankuplis, but look at the way he labeled now the streams. This is all labeled with subscript 1 for the bottom part of the tower, which is 1, and these are all labeled 2 for the top part of the tower. You have an equivalent of this in the handbook as written here on the slide. So they are figure 14.3 for the figure and equation 14-12 for the equation. So meaning they can be found in section 14 of your handbook. Now, the location of the operating lines, the lines that we form whenever we plot the mole concentrations of the phases on the bottom part of the tower and on the top part of the tower. So this is our operating line, where the equilibrium curve or line is a line or a curve that graphically illustrates the relationship between X and Y. When plotted together in one graph, so the operating line for gas absorption is written on top of the equilibrium curve or on top of the equilibrium line, and that of stripping is in here. So notice wherever we represent a particular column, you have to use the concentrations. You have to use the concentrations, and they come in pairs so that you will have a particular point in your graph wherein you can connect with another point, so as you will be able to construct the operating line. So 2 points using the concentration so that you'll be able to plot the operating line. So look very intently that the top is still 2 and the bottom is still 1 in the case of stripping. Now, this time, since this is review, we will not anymore use the graphical approach and finding the number of stages for a gas absorption tower or for the stripping tower. What we will use is the Krimser equation. The Krimser equation utilizes the mole fractions in the liquid and in the gas phases, whichever is needed, and the gas absorption factor. When the gas absorption factor is 1, this complicated equation is simplified in this form. Now, if A is a constant, which means that your operating line is really a line, then there's no need for us to get the geometric mean of the absorption factor of the top and bottom parts of the tower. And speaking of this gas absorption constant, you have the L over V as the ratio, as the slope rather of the operating line, and M as the slope of the equilibrium curve. So Krimser equation can be found in your handbook in this equation 14-33. Now, if the equilibrium line is curved, meaning it's not a line, then your M for your curve will vary. Correspondingly, your A will vary. So this is what I mentioned, that you need to get separately the gas absorption factor for each part of your column and get the geometric mean. In the formula, however, you get to see that you still have an M here of the equilibrium curve, which varies. So what particular M will you use in this case if M varies? So it is suggested that the slope that you will use is the slope of the equilibrium line on the dilute end. So you have to find the dilute end of your column, project it on the curve, and get the slope of that of the equilibrium curve at that particular portion. So you use the slope of the equilibrium curve at the dilute end if your equilibrium curve is not a line but rather a curve. For stripping, we have this formula for the number of theoretical stages. If A is equal to 1, this would be the N. In stripping, we have the stripping factor S, which is just the reciprocal of 1 over A. And you have that particular equation available also in the handbook for stripping. Now, we have a sample problem here for the determination of the theoretical number of stages. And this one is taken from John Copley. So just read through so that you'll be able to know how analytically Krimser equations helps us to find the number of theoretical stages for a particular problem. Okay, so from Krimser equation, so our solution this time is focused on the use of the Krimser equation. Now, there is this thing that there are problems rather that requires us to determine the minimum solvent requirement, or there are problems that requires us to solve for the optimum number of stages. The optimum number of stages is based on the minimum solvent requirement. So you cannot find the N optimum unless you know how to determine the minimum solvent requirement. How do we go find the minimum solvent requirement? In the case of gas absorption, all you have to do is in the point wherein you have the concentrations of the bottom part of the tower, you project it to the right. You project it to the right until you reach the equilibrium line or curve. Now, we say that we are constructing now an operating line which is made tangential to the equilibrium curve or line. And then we solve for the corresponding x1 maximum based on this particular transfer of point 1 to a point on the curve where it is tangential to. So how do we find x1 maximum? We use the equilibrium equation y1 is equal to m x1 maximum. So based on that particular formula of Henry's law, you can determine the x1 maximum knowing the y1 and the slope of this particular equilibrium curve. And most often the problem gives us the relationship between x and y. That way we can find x1 maximum using the m in that equation and the y that is specified in the problem. The same principle we apply if we have stripping. So for the point 2 in our operating line, what we do, we project it up until this line, this original operating line, is made tangential to your equilibrium line. So in here, we're trying to find the y2 maximum based on the x2. Still, we are using or utilizing the equation y2 maximum is equal to mx2. Given the m in the equation and the x2, we can find y2 maximum. So x2 has to be given and the equilibrium relationship for m should be given so that you can determine y2 maximum. Using the solve x1 maximum or y2 maximum for gas absorption and stripping, we will utilize the component balance equation wherein the inert streams are the one that are being multiplied to the mole ratios. That way, we will be able to find the V prime minimum or the L prime minimum depending on what the problem is suggesting. So there's a sample problem for that in here. So in absorption, recovery X1 is at the maximum when inert solvent flow rate is minimum. And this one we determine from the component balance equation, as I have mentioned, utilizing inert streams and mole ratios. Correspondingly, we apply the same principle for stripping. So recovery Y2 is at the maximum when inert solvent flow rate is a minimum. So this time we are determining V prime minimum, not L prime minimum, because our solvent in stripping is the vapor phase, not the liquid phase. Now, speaking of the connection between minimum solvent requirement and optimum number of stages, so this is taken from your handbook. So the actual liquid to gas ratio, or shall we say the solvent circulation rate, normally will be greater than the minimum by as much as 25 to 100%. So meaning what we normally use is higher than the minimum computed value by 25% or even 100%. Now, optimization of the liquid to gas ratio in terms of total annual cost often suggests that the total molar, take note, molar liquid to gas ratio should be about 20% or 50% times the more than the theoretical minimum required solvent in the case of gas absorption. So in here, based on the range of values that we are allowed to multiply to the L prime minimum, we are using the maximum on the range, and that is 50% more of the minimum solvent requirement. Though 20% more is acceptable, but often in textbook, we multiply it by 1.5. Meaning we're utilizing 50% of the minimum value of the solvent. For stripping, the actual value, so we just invert this to solvent over the feed. Solvent over the feed. It's also 20 to 50% higher than the minimum. So we don't really get confused here, because both for gas absorption and stripping, we are using an actual flow rate of the solvent which is 50% more than the computed minimum requirement. Okay, I have here a sample problem that will solve for the minimum. It will solve for the minimum solvent requirement so that the optimum number of trays can be computed. In this problem, the answer is 4. So it's 4, and the solution is in here. So I have to again encode it using Excel and then have it placed in here. So this is the computation for determining the theoretical number of stages. So please go through the sample problem again in your spare time. So the optimum theoretical number of stages is 4. Now this problem already utilized the concept of the theoretical stages, the minimum solvent requirement, and the optimum number of trays. So in one problem, we have checked your understanding, or the understanding of 3 principles are already illustrated. Of course, the understanding of the material balances required is equally as important as the 3. Okay, now we go to the pack tower, the design of this pack tower. So this is how it's illustrated. The liquid coming in on top and the gas coming at the bottom part of the tower. Gas leaves the top of the tower, liquid leaves the bottom of the tower. Now in this pack tower, we have packing materials, and in the illustration you have samples of random packing materials. So these are samples of random packing materials, and if they're not random packing materials, they could be structured packing materials, in this case here. Okay, and I have placed in here videos. This was not shared to you during our class in SEPA during your time, so I have shared it here for you to know how gas absorption really occurs in the gas absorption tower, which is having packing materials. So please watch. Okay, so our gas absorption tower, in this case a gas scrubber, eliminates pollutants in the gas before the gas is exiting the column. The contaminated solvent liquid leaves the column at the bottom part. Now, should the animation video and explanation should not be heard, I will share with you through Canvas the actual videos, downloaded videos. Now we have tray tower, so this is just a section of a column which has a tray, and this is your tray. The gas flow through the openings on the trays up, and the liquid flows in the manner like this. So it goes down here through the downcomer, passes through horizontally the gas that goes up, and is guided through another downcomer here. So the guide is the downcomer apron, so meaning your liquid has to really pass through here. So in the process, your gas, whatever it contains, the component that needs to be separated from it is being separated from that component through the passage of the liquid here. So there are openings on the trays, so they are different depending on the design. So this is how a tray column functions or looks like. Now, our tray, if our pack towers can have packing materials which are random or structured, in the case of the tray tower, we can also have openings on the tray, which could be a simple case of perforations, or it can have valve cups or bubble cups. And this is an example, a tray which has valve cups. Okay, a supporting tray which has openings having valve cups. So I will share to you videos on how each of these particular openings in our tray tower allows the gas to pass through against a liquid that is going down the column. So our bubble cap is the most commonly used type of opening for a tray tower then until the 1950s. But due to problems in contacting of the gas and the liquid solvent and support problems when the column is too high because of the presence of the caps, this particular design was modified. So there are other openings that are being used to arrest this problem. So the video that was shown explains the operation of a sieve tower. It's the simplest because you simply have a tray which has perforations on it. The problem mentioned were two, and one is the weeping. All of the liquid does not pass through the downcomer in going down the column, but rather some passes through the holes themselves. So that's weeping. Another is entrainment. So for very fast velocity of gas, some of the liquid goes with the gas as it goes up the column. But nonetheless, in terms of cost, it's the most economical and it's the simplest of the three design. Now let me share to you the last. Sorry. So the last opening are the valve tray openings, and they address the problem with the bubble cups and also addresses the problem of the simple sieve tray design. So it addresses both the problem of the bubble cup and the sieve tray design. So in such a case, there is shall we say, a balance of costing and design problems. But still, there is, shall we say, pressure drop in as the gas flows up the column and pushes the valve when the flow rate is very high. So there will be corresponding pressure drop in that particular process. So now we go to the design of our column, and when we speak of the design, we are determining the column diameter and the height of the column. So the first part here of the discussion is in determining the diameter of the column. if we need to determine the diameter of the column, it's needed that we know the concept of the flooding velocity, because that's the main principle that we use, or theory, in designing how big our column should be. Now, in terms of the pressure drop and the flooding velocity, together with the tower diameter for a packed column, the usual design is 60 to 80% of the flooding velocity. And that is, we determine the flooding velocity and we multiply it to 60% of its value, to 80% of its value. What is used often is 50% of the computed value of the flooding velocity, so as to determine the tower diameter. Now, if a pressure drop is as in the problem, then we can compute it directly based on this formula. Though if it's not as, we still need to determine the pressure drop because it's needed in the determination of the flooding velocity. Now, the packing factor is needed in the formula for determining the pressure drop for the determination of the flooding velocity. And this one is taken from a table. This is the procedure in determining the column diameter using the pressure drop. So we obtain the packing factor from a table. This depends on the type of packing material that is being used. Then we determine the flooding pressure drop based on the formula provided in the previous slide, and the formula is this. Then after that, it is expected that our linear velocity, that is our linear flooding gas velocity, would be about 6 to 6 feet per second, or that would be 2 meters per second. Now we choose diameter such that the gas velocity is just about half of this. Okay? And our design, the usual design, is only 1 meter per second, which is not even half of the maximum linear velocity for flooding. Then we find the pressure drop in the column from pressure drop correlation figure. Now let me show to you the data that you will be needing and where you're going to get those data. For the packing factor, you have the simplest form of the table here, though you have a more comprehensive equivalent in your handbook. So the packings are grouped as random and structured packing, and you have packing factors on the second to the last column. So we use this on the determination of the pressure drop, and we use the identity of the random packing material. That way we can get the packing factor. So you have two values here, one using the SI unit in per meter, and the other is per foot of packing material. So the pressure correlation, or the pressure drop correlation, for both random packing and structured packing will be using unique tables. So one is only applicable for random packing and the other one for structured packing. Both utilizes the pressure drop that were determined in the formula that was given. So in the horizontal axis, we solve first the flow parameter. Then from the vertical axis, we get the capacity parameter. When we know already the capacity parameter value from the graph using delta P and the flow parameter here, we'll be able to determine the linear velocity of the gas when it is already flooded, or when the column is already flooded. Now let me check what you have here in order for you to be able to know the x and the corresponding value of the linear velocity here. So for the x value, you need the ratio of the liquid to gas, and you need the ratio of the density of the gas and the liquid. So this will be the formula in determining your x. As for the y, since you are going to read it using the delta P and the flow parameter x here, you still need the densities, you need the packing factor, and you need the kinematic viscosity. The kinematic viscosity uses the viscosity and the density of the gas. So if the problem is designing a tray tower, not a pack tower, you will still be using the flooding velocity. So all design on how big a tower should be, whether pack tower or tray tower, utilizes the flooding velocity. We get the tray factor K sub B from the figure, which will be shown to you in a little while, and we determine the gas velocity. And this gas velocity is given by this equation, also found in John Copley's. So the V maximum, or the entrainment gas velocity. Now, the most common value used for interfacial tension is 29 per centimeters for organic liquids, and for water it's 72. Now, the typical value range here that could be computed is 3 meters per second. How do we determine the diameter of our tray column? We choose a diameter so that the gas velocity is just around 70% of the computed value here in number 2. So whatever is your computed value in number 2, you multiply it by 0.7. That should be the velocity that you will be needing so that you'll be able to determine the cross-sectional area of your column. Knowing the cross-sectional area will allow you to determine the diameter. As for pressure drop, this is usually much larger than in packed columns because of the pressure drop for gas to pass through the liquid on the trays. And delta P here is equal to the delta P dry gas plus rho L, the density of the liquid, G times H. So the delta P dry is the pressure drop through the holes of the tray. That is no liquid yet passing horizontally through the holes. The H is the sum of the liquids on all liquid levels on all trays, which is about 10% of the column height. So the column height in this case needs to be given by the problem or predetermined. We multiply it to 10%, and that would be the H that we will multiply here to rho GH. If you recall in your elementary physics, fundamentals in physics, the pressure is rho GH. So rho GH, density, the gas acceleration, or the, shall we say, the 9.8 meters per second, and H is the height. So that H here is 10% of the column height, which should be given by the problem or predetermined. The KV is taken from this graph, which utilizes the abscissa value pre-computed. So you have to determine this first so that you will have an X value, and the tray spacing in the problem. So the tray spacing is mentioned in the problem. And then with that value and this, you'll be able to get the KV, which you need to use in here, so that you'll be able to determine the V maximum, or the flooding velocity, when interfacial tension and densities already are known and substituted to the formula. Now, as for the height of the column, so you have several formulas and several methods of finding the height of an absorption or stripping column. If it's absorption class, in your handbook you have equation 14-15. You will utilize the HG product, which has the subscripts G or OG. And I often call this the hognog, and this one the HG and G. If it's gas absorption. If it's stripping, you use the HLNL or the Hall null. Now, what does this NG, NL, and OG represent? NOL? So, number of gas phase transfer units for NG. So, if it's L, number of liquid phase transfer units. NOG is the number of overall gas phase transfer units. So, the O represents overall. And the O here, the same thing. But in here, it's number of overall liquid phase transfer units. HG and HL determines the height of one transfer unit based on the gas if the problem is gas absorption, and based on the liquid if the problem is stripping. So it accounts for the gas phase and the liquid phase resistance. Okay, the two heights. The NOG in the formula you just saw, or the NOL, can be solved using the absorption factors, and the process of determining the absorption factors were already illustrated on the topic of determining the theoretical number of trays. In your handbook, you have this formula made available for you in determining also NOG, NOL, HOG, and HOL. This one is the one snipped from John Copley's. The equivalent are these equations in your handbook. So what you do, once you have already the NOG and the NOL, you get also the HOG and the HOL. Multiply the two, you will have the tower height. That's one of the procedure. Although if the tower is, shall we say, using overall mass transfer coefficient, or is using the concept of the film coefficient, the mass film coefficients, then Jan-Kuplis gives you the equations here. So equations 10.6, that's 27 to 32, and equation 10.4-23 to 27 also. This is for dilute solutions. For concentrated solutions, we have this equation. Now, the use of these equations determines the height using the slope. The slope of the point on the operating line connected to the point on the equilibrium line, as illustrated in the sample problem that is inserted here on the slide. So the varied procedures for determining the tower height using this method and the previous one are illustrated in that particular example problem, together with the other method which will be mentioned here on the next slide. So in that method utilizes the HETP concept, and that is the height of packing equivalent to one theoretical stage. So if you intend to not to solve the Z using the HG or the HL, the hug or the nug, the hull or the null, and you don't want to use the suggestion also of Jan-Kuplis for dilute and concentrated solutions using the slope of the points mentioned in the previous slide, then this one is for you. Although it will still be using part of the procedure that is used in the process of Jan-Kuplis. So HETP will need the hug, because in the formula you have the nug and the gas absorption factor found on the handbook on this equation. The nug here is equal to N ln A over 1 minus 1 over A, and this is equation 14-34 also in your handbook. The Z here using the HETP process is, the Z rather is using HETP times the theoretical number of stages. The theoretical number of stages uses Krimsker's equation. The HETP uses this formula that you have here. In the formula, you have the nug, and in the nug, this one is a formula for the nug that you have in Jan-Kuplis, or you can use this formula here for the nug as well. Now, so this is a sample problem that majority of you have already encountered in our discussion. I did not anymore look for a different one, because in itself the discussion of determining the tower height for this sample problem is already very comprehensive, showing to you all 5 different procedures. So that procedure of finding the value of 1.36 for the tower height based on the 3 methods, the HGNG or the dilute concentrated formula method and the HETP, are all on this particular solution inserted here in our slide. So you have here the explanation of that line that I have mentioned, wherein the slope is using the film coefficient, gas film coefficient. If it's small letter, that's just based on on the gas phase resistance. But if it's capital letter, then that would be using the overall gas phase resistance or the overall liquid phase resistance. The difference in the computation using the given mass transfer coefficient, film coefficients in small letters and capital letters, are illustrated in one of the procedures here. I think it's in this procedure number 4, wherein from the mass film transfer coefficient we determine the overall mass transfer film coefficient because it's capital. So don't make a mistake of using the small ky prime a to capital ky prime a. They are different, and the capital uses both the small letter k sub y prime a and k sub x prime a. Now, if the problem is gas absorption, you use the k sub y prime a. It's given in the first procedure. If the problem is stripping, you use the k sub x prime a. Nonetheless, if you, let's say for example, you use the k sub x prime a, even if the problem is gas absorption, you will notice that the difference in the answer is really very small. So meaning, if you use this one, even if the problem is gas absorption, your answer will still fall near one particular value in the choices provided. So hindi siya maglayo. So this would be the last part of our slide. I suggest you read through, you complement what is discussed here in gas absorption on what's available on Janku, please, especially on the design part of the column, because most problems in the board exam does not only determine material balances but the design of the unit operations equipments. Thank you for listening, class, and I will be recording the last two for this part 2 later and have it as well shared to you.